Good evening, everyone, and thank you for showing interest in the subject that we've submitted. I'm actually impressed in the number of people that are still here because we are covering the last slot of the day. We've made actually some bets earlier. Tiberiu said something about around 50 people. I'm the pessimist of the group. I said I bet there will be no more than 30 people. So I guess he won. And I owe him like 2 pounds of French fries because this dude sits outside the norm. I'm pretty sure you would have expected me to owe him like a 6-pack of beer, but his kryptonite are French fries. So, yeah. My name is Marius Monica. I'm part of the Adobe Security Coordination Center, where I'm mostly responsible for IR-related activities. This is Tiberiu Boros, my colleague. He's part of the security intelligence team at Adobe. He's mostly responsible for ML-related stuff. So the topic that we are proposing today, it's actually an alternative approach of classifying scripts as being malicious or benign. The project is called Scout. I'm responsible for picking the name. He's responsible for mapping machine learning notions on each of the letters in the name Scout. So basically, Scout means simple classifier over unsupervised tokens. Yeah, it's impressive. Huh? Cool. Now, before continuing with the presentation, I want to say that we did a couple of dry runs yesterday in front of a part of our colleagues, and the feedback that I've received was that, dude, you have no idea on how to use intonation when you're giving a presentation, and you lack enthusiasm. So even if in the middle of the presentation I'm going to start doing some Michael Jackson trick voice, you now know the reason, okay? So, yeah. Okay, so for our proof of concept, we've chosen JavaScript for several reasons. I've started initially researching. I've started the research for this presentation in mid-October. I found some information which situated JavaScript in terms of client-side programming languages that are used on websites at around 95.1%. So this is the current market position. Being this present in the web, it mostly embodies the common attack vector when it comes to evil-minded attackers trying to get access to victims' computers. I'm not saying per se that JavaScript frameworks are in any way, sort, shape, or form vulnerable to anything in particular. I'm just saying that it's easy to use JavaScript because as an attacker, it's easy to blend in. So some of the popular frameworks that I'm pretty sure you already know that we focused on, and will encompass some of the data set that we are going to present in a couple of slides. The good data set is based on some of the JavaScripts that were pulled from these repositories. Cool. In terms of vulnerabilities, these are quite common when it comes to JavaScript. I'm pretty sure you are all familiar with with the notions that we are showing on the screen. I've sifted to a couple of security reports which were shown this year, and JavaScript is currently used as a common attack vector. Most of the headlines that I've seen were related to form jacking, which was quite popular this year. Apart from that, we had a lot of JavaScript downloaders and CryptoWall, which was a variant of a ransomware used as initial infection vector, a JavaScript file. So it's actually commonly used, and it's not only targeting like websites, it's also targeting individuals or enterprises. These vulnerabilities that we are currently showing being not only client-side issues, but also enterprise nightmares. So the detection methods that we are currently employing when we are performing analysis are, as I'm pretty sure you already know, static and dynamic, and are based on the current execution state of the script. So when we are talking about static analysis, we are referring to the static features of a script and its structure. And we are referring to, when we are referring to dynamic analysis, we are actually executing a script in a control environment, and we are monitoring for known stuff like ports, network connections, system configuration file modifications, and or registry modifications. And what we are currently trying to propose with Scout is a somewhat different approach, because Scout uses, as a method of detection, a static way of analyzing things, but which is not relying on any sort of explicit rule. And it has two main components: tripod, which is the actual brain of the project, and TB will cover it in the next slides, and a simple multi-layer perceptron.
Okay, guys, so I'm going to be covering tripod, and I'm going to start by saying that basically the main topic in machine learning today are latent representations, and I think this is a good starting point to, begin by defining them and say what makes them good and what makes them bad, how you do distinguish between them. So for that, do we have a mic, mobile mic? Yes. I'm going to need a volunteer. Does anybody volunteer? I'm going to choose that guy. Yeah. No, just sit, don't worry. Okay, so wave to everybody so they can see you. Come on, come on. So we know each other. His name is Alex, but I spent half of the day convincing him to come to this presentation. He had no idea that he was going to be abused here. So we're going to start by playing a little game. I'm going to show you some pictures, and you're going to tell me what you see in them, right? Okay. So just look at the pictures on the right, not the one on the top left corner.
I'll try.
Of this slide, right?
Yeah.
What do you see?
Cats.
Do you want to save him? Anybody? Are all? So cats? Dog? Who said dog? Okay, one dog. Where's the dog? This one is a dog, right? Do you know how you know that's a dog? Sorry, Alex. Okay, so basically you know that's a dog because you have a good, huh?
He's more happy.
He's more happy, yeah, cats are always sad. So this means that you actually have a good internal representation of what a cat is. You already know that it's furry, it has pointy ears, and most of all it goes meow, it doesn't bark. Barking would be a dead giveaway that that's a dog, right? So basically what an latent representation is, it's a vector of real-valued numbers that tries to capture abstract features from the input data. Now, the more abstract the features, the better the latent representation, which means that actually this representation over here is the perfect representation of a cat. If you'd be able to train a network that would see that when it sees a cat as an input, that would be great. Well, in reality, it probably looks something like this, which is an abstract representation of an abstract representation of a cat. But, that's good enough. So, this is just for show. It doesn't really mean that that's what networks do. It could be worse than this. Now, one of the main, the most important features of latent representation is that they have to be separable and coherent, right? So, we rendered a couple of digits over here. So we have ones, sixes, fives, threes, stuff like that. And we rendered the latent representation of in bidimensional space. This is actually something from a variational autoencoder, I think, or TSNE, I don't remember. But the idea still holds. So you want the input data that looks alike to be in the same space. You want them to be really close to each other. And you don't, you expect something like to have a 6 that looks like a 5. That's OK. That happens. On the 5 that looks like a 3, which is all the points over here. But what you don't want to have is a 6 that would actually create a latent representation that would be close to a 1, right? Because if you have a network that learned that, that means it didn't learn anything. So you have a problem with the data. So the same thing applies for words in natural language. So if you're building latent representation for words, you'd expect that words that have similar meanings or that appear in similar contexts to be really close to each other and further apart from the other words. So now let's get to tripod. Do you still have your mic?
Yeah.
Okay. I'm thinking of a sentence, and I'm going to give you a clue.
Okay.
And you're going to tell me what sentence I'm thinking of, right?
I'll try.
Okay. This is the clue.
The quick brown fox jumps over the lazy dog.
Is that okay for everybody? Why not?
There should be a cat.
Yeah, that's good enough. That's good enough. But okay, this is not the sentence I was thinking of. I was actually on the way here. Marius told me that this sentence is overrated, or for him, foxes are actually red, which is really good. But dogs are usually lazy if they're fat. So what could my sentence be? Oh, come on. The fat dog. Okay, so these were the two sentences. Great catch on the red, yeah, really. So let's see what happened. When you saw my clue, you immediately thought about the quick brown fox jumps over the lazy dog, because you saw that sentence a lot of times. You probably already memorized it. You've seen it everywhere. It's been used in, I think, Microsoft speech recognition to tune your system and stuff like that, so that's awesome. But you didn't know what I was thinking about, because you're missing something called context, because I told you the story, and you already, you began to guess what I was thinking of. So this sentence is from memory. Those two words, come from context. When you had context, you're able to replace them and to guess exactly what I was thinking. And now there are many sentences that have the same skeleton. So we have the quick fox jumps over the dog, and you can say the quick red fox jumps over the blue dog. You can say the quick red fox jumps over the old dog. Yeah, they are the same. So basically, you have three types of representations here, right? So this is getting back to Tripod. Tripod is a machine learning toolkit that is open sourced. It is used to compute latent representations for sequences, right? So it builds the three representations that we talked about. So we have the memory-based representation, the context, which we call summary here, and the GST, which stands for global style tokens, but it's the style representation, right? So what it does, it uses a trick that is used in many unsupervised machine learning algorithms that try to learn latent representations. And it has the input data, it computes a latent representation for that, and it tries to reconstruct the same input data based on that representation. So that representation is called a conditioning vector. And Tripod computes the conditioning vector using something called an attention, the attention mechanism. So what the attention mechanism is can be easily shown by taking these two examples. So we have the two standard machine learning approaches to image captioning on the left and machine translation on the right. So we have English and French, and we have those images, and the model has to guess the sentence word by word. So attention actually allows the model to focus on a small portion of the input whenever it generates a new token. So when it says frisbee, this is, I don't know if you can read this. Is this readable for anybody? Okay. So when it says frisbee, it focuses on this portion of the image where you have a frisbee. When it says dog, it looks under to the dog under the bed, right? Okay. So this is basically Tripod. Tripod computes three attentions. The first one is over the input sequence. This is actually the model. It's a standard encoder-decoder. It takes the input, it computes an attention over it, and it tries to reconstruct it, and this actually creates the context, right? Now, it turns out that you don't have to apply the attention over the input necessarily. You can actually use vectors, a fixed number of vectors, and if the number is really small, like 20 or 30 or stuff like that, the network would have to generalize and actually learn to map skeletons of sentences to these vectors. So this is where you get the style. And the last part, the memory part, is really easy because you can always overfit a model. So each time it sees something that it has seen in the past, it will know it has seen it, This is done, in our case, by applying attention over a really large number of tokens, right? Now, the project is open sourced. We have a pip package installation. We have also Python API. You have just to import the API in Python, create a new instance, tell it what model to load. We provide pre-trained model for English, Romanian, and also JavaScript, which is actually the base of the rest of the presentation. Once you've loaded the data, you just have to apply it, with the model, you just have to apply it over your data. You just call this method over here, and you get data in a presentation. And to show you how this works on JavaScript, we have three really simple examples. So the first two, you can see them over here. So we have example 1, example 2, and example number 3. The first two are just basic for loops with a conditional print, and the last one is really an optimal sorting algorithm, right? So over here, we rendered the tripod vectors. We projected them into a bidimensional space. And this is the general representation composed of by concatenating all the three vectors inside one and reducing the dimensionality. This is the summary-based representation. And these are the style tokens and the memory-based representations. Now, if you look at the summary, you see that the vectors are further apart, right? So this is because they use different variables, the condition is inverted, and there are slight differences in the way the code is written, right? So we have brackets on top, we don't have on the bottom. But when you look at the style and memory, the first two examples actually collapse. This is a vector which is composed by the two collapsing vectors of the first two examples, which is good, because basically the code does kind of the same thing, right? So this also works for text. We have two sentences that, from Wikipedia that speak about science and mathematics. The first two and the second two, something to do with administrative and stuff like that. So we have the overall vectors, which we're not going to talk about because it doesn't really express anything. But we have the summary, which says that the first two sentences are really close to each other and the last two sentences are really close to each other. And when you look at the style, on memory-based representation, you see that actually the first and the last sentence are close to each other, and that's probably because they are definitions of something. So basically, this is tripod. I think Marius can...
I can take it from here. Yep. So we've tried to formalize a bit the process. So this is the machine learning project life cycle. So we've wrapped our efforts around the stages that you can see on the screen now. We've spent the most of our time in gathering the data and exploring and prepare it for the project. So we've encountered some challenges when building the data set because we've needed enough labeled data, good and bad, for our project because this was the specifics of it. And one thing that we've learned was that data is the most crucial aspect of a machine learning project. No matter how good your AI team is, and trust me, this guy is really smart, your project will actually fail. Second of all, you will spend a lot of time on exploring the data and preparing it, because machine learning is not all about large data sets. You have to feed the system with carefully curated and diverse data. And after that, you have to model the data that you will be using for prediction and make sure that you communicate the results in a manner that's clear and concise. Now, what were the specifics of our project? Before going further, I would like to mention that all the resources that we've used will be mentioned on the last slide of the presentation. For creating the legitimate data set, we've sifted through a lot of GitHub pages of known popular frameworks, basically the one that I've listed on the first slide. So jQuery, Node, Angular, Vue, Mithril, and stuff like that. We've extracted JavaScripts from there and created the legitimate data set. And then we were lucky enough, and one of the reasons that we focused, or another reason that we focused on JavaScript was because we were able to find a couple of repositories on GitHub which stored around 40,000 malicious JavaScripts. But keep in mind that those repositories were created around 2016 or 2017. So initially we had the good data set and the bad data set, and we ran our initial tests on them, and the results that we've obtained weren't satisfactory, meaning that we were able to classify malicious JavaScript with an accuracy of 0.99%, one being the maximum of it. So we then returned to the exploration part, and we found out that the vast majority of the scripts were obfuscated. And then we've spent a lot of time trying to replicate and mimic obfuscation techniques that were used in our bad data set and include them in the actual corpus because we wanted to build a robust data set. And we wanted to avoid that every time we run Scout against an obfuscated script, it will be automatically flagged as malicious, even though the script wasn't malicious. And now that I'm mentioning that, I'm thinking at least of a couple of reasons that one might want to obfuscate, let's say, a legitimate script for size reasons or for hiding business logic or code and code. Cool. The pre-processing part of it included a suite of techniques. So we focused a lot of minification, which is the process of removing all the unnecessary characters from a script without tampering its functionality. We've targeted comments, white spaces, lines and tabs. When we did finish this part, we moved on to obfuscation, and we were able to find an open source tool which is called JavaScript Obfuscator. This tool provides several ways of actually obfuscating scripts. So we focused on base64 hexadecimal obfuscation and mangle obfuscation, as they call them. And apart from that, we found out that another obfuscation technique that was highly used in our malicious data set was the appending of certain symbols inside the script. So what we did, we've actually appended commas and quotations after each character on a subset of the data set, after sequences of 2 characters, and after sequences of 3 characters, because that was the actual specifics of our data set. And when we were done and satisfied with the obfuscations that we've employed so far, we moved on to character code sequences, because if you remember, and I'm pretty sure you do, Tripod works on character code sequences. So what we did, we actually, from the whole master data set, because that was the name that we've used, we've split it and created 1,000 characters code sequences. And we've also labeled them with 0 if the character code sequence was good, and 1 if the character code sequence was bad. And then the next step was actually to run Tripod on all those character code sequences, and Tripod took care of the vectorization part of it. In terms of model implementation, one thing that I would like to emphasize before explaining the logic flow, which is extremely simple, open source and user-friendly. These are the main things that you should keep in mind. So we've used two libraries for our multi-layer perceptron, which is a class of neural networks that has at least one hidden network, TensorFlow, which can be used on all platforms, Windows, Mac, Linux, and Keras, which is a library written in Python that can be used for fast experimentations with neural networks also. So if you want to gather more information about this particular libraries, we highly encourage you to visit their official pages and find more about the features and how they can be actually used. And if you search like Google, you will find a lot of projects which are based on Keras and TensorFlow, because these are two powerful, really powerful resources. So what you're seeing on the screen is basically our multi-layer perceptron, and that's why I've said that is a simple solution that we've used inside Scout. And the logic flow is quite straightforward. So we had the good and the bad scripts, which we fed into Tripod. Tripod created the vectors, which we've labeled here as our data set, and then we use the multi-layer perceptron in the training phase. Now results. And I have to make a few mentions here. So we've run Scout on an unseen data set, which was composed of 42 benign scripts and 42 malicious scripts. What I would like to mention here is why did we call it an unseen data set? I mean, it's a common machine learning thing. It's because this particular data set wasn't part of the training set. So you have to keep in mind this. We've created a separate data set which was composed out of other malicious scripts which employed, let's say, more novel techniques in terms of obfuscation, and we've worked hand in hand with our threat intelligence team to create this particular data set. And I'm going to explain the results that we've obtained on that unseen data set. What you're actually seeing here is the results that we were able to obtain on the actual training set. So the results that we've obtained on the training set were a bit higher on the training set and test set, up to 0.97% accuracy in terms of detection. But when we've run Scout on the unseen data set, the accuracy per segment, so those 1,000 character code sequences, was situated at around 0.91%. And what we did afterwards, we've applied some sort of logic because we've intended to increase the accuracy in detecting those malicious scripts. So we've employed a couple of if statements. I'm going to give you some examples in order for you to better understand what we did here. So we've said that if a particular script contains like 4 segments, and out of those 4 segments, 3 of them are flagged as being malicious by Scout, then the whole file will be considered as malicious. If we have, for example, a really big web page which was injected with a segment, and we run Scout on it, and the score that we are getting out of only that specific segment, it's like 0.99%, then we're going to flag it as malicious per se, even though it contains only 1 segment, but the score is really, really high. And a couple of other things. But you can actually modify to your needs this specific logic. Maybe if you're obtaining scores like around 0.5%, 0.4%, and a couple of the segments that you identify bear this specific result, maybe you might want to flag that file as being suspicious and not malicious, and analyze it afterwards. Cool. But you don't have to actually trust these results.
So it's 91%, it's not 0.91.
Yeah, 91.
It's 91, not 95.
I said something about 1 being the max score.
Okay.
Yeah, I mean, you don't have to trust us. It's open source. Just run it on your machine, and I think it will do. It will do the job. Cool. Now, some of the conclusions that we've found during this project. It's like there is space for machine learning. There is a place for machine learning in the security space. Apart from that, we found out that data and the time you spend processing it is actually the most crucial aspect of a machine learning project. And I'm going to let TB make a few mentions about Tripod.
Okay, so Tripod is open sourced. If you guys want to contribute to it, you can contribute by training your models, maybe making them available for other people who are part of the community. Also, if you want future requests, you can just go to GitHub, file an issue, ask for resources, data, anything you want, and also give us a star on GitHub. Thanks.
Yeah, and another mention that we would like to make, so we weren't the only ones who worked on this project. If you remember, there were 3 names on the initial slide, so we had another member of our team who spent a lot of time on this project, and this dude is like sitting right here and judging us because we haven't called his name so far, so his name is Andrei Cotaie, and he had some contributions to this project. Yeah, and I feel like I need to mention 2 more things. So when we've worked on this project, we've encountered a couple of limitations that I feel like I need to bring up. So one limitation is like the unavailability of malicious repositories that you can use in order to train your model. And the other one, let's say, it's related to obfuscation techniques. So we've trained Scout on a finite number of obfuscation techniques. And if tomorrow, let's say, I've heard like APT25 being a thing these days, comes up with a new technique of obfuscating these files that it's going to be able to hide the structure, we might not be able to highlight that specific script as being malicious with a high accuracy. But keep in mind that Scout is a work in progress type of a project. So we, or you, if you find new techniques, or we, if we come along with new techniques, we can create specific data sets which use that technique, and we can train Scout on those techniques. And thank you.
Thank you for the presentation, guys. And I think you can notice how much it was appreciated by the number of hands that started raising before you were done. All right, let's take a few questions. Can you take a question from the right side?
Phone. Sorry, I don't know, the sound is working? Yeah. I think I have two questions, actually. The first one is related to the training part. Like, you said that it's open source and I can download it and use it in my own project. So what happens if, after I download it, I use it in my Python script, and the training section, what would be like? It's already trained, it's gonna start from scratch and it's gonna train based on my samples?
So basically, we have two parts of the project. So the first one is Tripod, which is able to extract latent representations from JavaScript, and you can probably train it on any other languages. And the second one is actually the classifier, which tries to classify based on the extracted representation if that's malicious or not. Now, I know that Tripod is open sourced. I don't know if Scout itself is already out there, and it is, isn't it? So Scout is not actually open source, just Tripod.
Okay, so just
next week.
Next week. And the next question would be like, did you perform any tests against the most classic metinterpreter stuff, the delivery mechanism using the JavaScript?
No, the answer is no, we haven't.
Should you try?
Of course. I mean, you just send me an email, Ciprian.
Yeah, failed. Thanks.
All right, next question.
Yeah. Hi. Yeah, great job, by the way, with this tool. I have a question related to an Adobe product, actually. I would like to know, when you guys going to rid the world of the pest called Flash?
We already did.
No, I mean for real, not just promises. When are you going to pull the thing and bury it?
It's already dead, from what I know.
Don't shatter his hope.
Yeah.
All right, let's take another actual question. Here at the front.
Hi, very good presentation, thank you. How can we use this to limit false positives in static code analysis, for instance? Because you mentioned that we can go and use it in Java or C#. Can we use it? How hard is it to port this to?
So basically, we have a Python API. You just feed it some random size of code, sample of code, and you say compute something based on this, right? And then what you do with that data, it depends on you. So if you want to classify between malicious or non-malicious, maybe you have a different data set. You just build your own multi-layer perceptron, use your own data, or just wait for Scout to be open sourced. But I believe that everybody has. We relied on stuff that was already out there, and I think that most companies have their own repository of what they deem as bad and good, which would probably be a better idea to just train it on that.
Okay, thanks.
Two questions. The first one would be generically, what were you using and how long the training went? And the second one is, did you often encounter the situation when the network collapsed during the training?
Well, the training didn't took that much.
So training Tripod took like 3 days on JavaScript code. And JavaScript, I mean, basically the multi-layer preceptor is really fast. Marius can give you the numbers if you want to. I mean, it's really close.
Okay, and about the collapsing the network being collapsed during the training, did you encounter these problems?
I mean, we didn't have that problem with the multi-layer preceptron. We actually had that problem with Tripod because we trained it on some application logs. And it collapsed when you did that, but it has an option when you train it to reduce duplicates, because that's what the problem was, and to actually do something called partition dropout, which makes it usable for application logs that repeat it themselves.
Okay, thank you.
Come on, we have time for one more question if there is one. Let's go on the left as well, because we haven't had any from here. It's a long way down left.
Hey, so thanks for this. It's nice to see realistic machine learning. Why'd you guys choose JavaScript as opposed to PowerShell scripts? And have you considered using, for example, Word2Vec to apply this to other data that could be used in threat hunting?
Well, I can take care of the why did we actually choose JavaScript. I mean, first of all, because we've focused on open source things that were already there. So we were able to find those repositories which held around 40,000 malicious scripts. So it was easier this way. And second of all, due to his presence, as I've mentioned initially, because it's highly used. And Word2Vec.
Okay, and the idea is that Word2Vec actually computes latent representations for tokens, not for entire sequences.
Oh.
You need to use paragraph2vec or document2vec, and we actually compared Tripod with paragraph2vec on a standard natural language inference process, and we got an absolute increasement in accuracy of 5 to 7% on the SNLI dataset from Stanford.
Oh, cool. One quick thing. Have you considered using retro hunting on VirusTotal to find more data?
No, we haven't.
I didn't.
Yeah, thanks for the suggestion.
Yeah, you could do that.
All right, thank you so much for this presentation. It's going to go down in history as having questions already from the last quarter going forward. Thank you.
Thank you.
Welcome.